Hello everyone and welcome to our digital days. My name is Markus Eberle and I will moderate this webinar today. We are very pleased that you took your time today to listen to our virtual conference and this presentation. Our topic of today is single pair Ethernet with signal transformers. Our speakers today are Martin Leihenseder and Simon Mark. They will hold today's presentation and also will answer your questions today. Before we start the webinar or also our presentation, I would like to point out one thing. You will be muted during the presentation today. This means that you cannot ask us questions via microphone. Nevertheless, you have the opportunity to ask us questions with the chat function. You will find the chat function in the webinar control panel. The presentation will be about 30 minutes long. Your chat questions will then be answered in a question and answer session after the presentation. We have scheduled for that also 5 to 10 minutes. And if we are still unable to answer all your questions within this time, we will answer them via email after the webinar session. And if you still have any other questions left, just email us at exhibition@we-online.com. At the end of the presentation, you will be asked to participate in a feedback survey. Of course, we would be pleased if you help us to improve our virtual conference. You will also receive the link to the presentation you see now just in the next few days. The recording will also be available at our website shortly. And now I would like to hand over to our speakers and first to our speaker, Martin. And I wish you an exciting presentation.
So, can everybody hear me? Hello and welcome also from my side. My name is Martin Leihenseder and I'm Senior Product Manager at Würth Elektronik eiSos in Waldenburg in Germany. And with me today is my dear colleague Simon Mark. He is Simulations Manager and he will do the part of Power over Data Line for today. Yeah, when it comes to single pair Ethernet, then what we are doing as Würth Elektronik eiSos is only a very small part of the whole system. We are doing the filtering, but although it's a very small part of the system, it's a very important part because without the right filtering, you will have EMI issues in your design. You will have, you cannot reach an isolation or other things like ESD issues. Yeah, so the filtering is very important, and therefore in the last months or even in the last years, we really were working strong on single pair Ethernet and what will be the perfect filtering for this system. The agenda for today is that first I like to give you a short introduction for the single pair Ethernet for all of the ones that never had thought about single pair Ethernet or never worked with single pair Ethernet. After the introduction, we will talk about the signal filtering. So what are the problems that can occur with the filtering? Yeah, what kind of thoughts we had to make this filtering true? And we start with 10 base T1, 10 base T1L. This means 10 megabit data rate over 1,000 meters. And then later on, we go over to 100 base T1. And the second part of the presentation is about power over data line. We already provided you many information in the last presentations, but we have also new content with us, and this will come from my colleague Simon. So we show the function of the components. We show also what we have improved in the last months with the design, and we have brought with us some solutions for high currents so that we can provide solutions for all pool classes. And here's something that was asked at the last sessions that we had. What about 10,000 base T1? Do you have some solution here? And also here we want to give you some information. End of last year, we have done some pretty campaign together with 2 other companies or with 3 other companies. We worked together with Analog Devices and Harting on a Mouser campaign. And I was thinking these slides that we made for this campaign, this is a perfect start to introduce single pair Ethernet. And so here what we can see is is a connector. This is a connector for single pair Ethernet and a cable for that. And what you can see is that the cable has only 2 lines. And this is the big difference to the standard Ethernet, while at fast Ethernet with 100 megabit per second with 4 lines, and with gigabit we have 8 lines, we now have only 2 lines. And with this change, there are of course challenges in designs, but there are also many improvements that we have on the other side. And these improvements, disadvantages, I like to tell you here. Single pair Ethernet is more. This was the name of our campaign, or this is the name of our campaign. And what does this mean, single is more? And here's some explanation for that. So first of all, single pair Ethernet provides more reach compared to the standard Ethernet. While at standard Ethernet we have up to 100 meters of reach, with single pair Ethernet we can provide 1.7 kilometers of reach right now with the PHY chips that are on the market. For example, from analog devices or with Texas Instruments. Speed, we have more speed. This is more speed compared to the field bus systems that you have right now in the factory. Nowadays, many sensors, actuators, cameras, and so on, they are connected with field buses, and single pair Ethernet can provide up to 1000 megabit per second. This is not more than the standard Ethernet, but it's the same like standard Ethernet. Of course, you think, okay, there's 10 gigabit per second is also possible, but this is not working normally with industrial Ethernet protocols. So here the limit is 1000 megabit, and also a single pair Ethernet can provide this. We have weight saving, and we are cost effective because the cables are thinner and there's less copper needed to provide the data. And so when you can save copper and space, then of course the cost is reduced if single pair Ethernet will come in high numbers at the end. We have a miniaturization. This is based on the small connector that we have. This very small connector is also very robust compared to what we have at the standard Ethernet. And also the filtering is much smaller, as you can see in the following slides. A very important point is simplicity. And what I do mean with simplicity. This is what you can see on this slide here. This slide shows some standard factory like we have it right now. Normally, in the IT area, you will see a lot of Ethernet as communication, and this Ethernet goes until the factory area. In the factory area, we have also Ethernet, but it's another Ethernet. This Ethernet is industrial Ethernet, and those protocols, they are time sensitive. So real-time Ethernet is possible in difference to the standard Ethernet at IT level. And this industrial Ethernet normally goes into the shielding cabinets or to the robots. But on that point, there we see a very different picture, because at this level, we have many different field bus systems working together. We have Profibus, CAN-Open, CC-Link, and others. And all these systems provide a different data. And on a certain point, and this is the gateways, this data needs to be transferred in Ethernet. Why this data needs to be transferred in Ethernet? Because those field buses they cannot provide the data to the cloud. They need to be transferred. Yeah, and those gateways, they are complex, they are large, and they need a lot of energy, and this makes the whole process very complex. And of course, for maintenance, this is also not very easy, as the operating engineer needs to figure out different systems. With the single pair Ethernet, the picture will look different. Yeah, also here we can see the standard Ethernet in blue at the office area, and on a certain point also the industrial Ethernet, but every sensor, every actuator, every camera can be connected with single pair Ethernet. And then instead of the gateways, we will have normal switches, because the data that single pair Ethernet provides is the same data that also normal Ethernet is using. And so we can provide a seamless communication from sensor to the cloud. And this makes it very simple. for the operators, for the engineers to do maintenance in the factory, which is also cost effective at the end. Now let's just give me a second. I change here to laser pointer, then you can see better what I'm pointing on. Okay, thank you. Good. So here a few details about single pair Ethernet. Single pair Ethernet, like I said, is a bit different to fast Ethernet or to gigabit Ethernet. At fast Ethernet, you can see we have two pairs of wire. One pair is the transmission channel and one pair is the receive channel. At gigabit Ethernet, we use all 4 pairs inside a cable, and this means, yeah, we have the 4 pairs of wire. But here, every channel is transmission and is receive channel. Yeah, so we have duplex mode here. Bidirectional communication is here. Single pair Ethernet is using the same technology. So also here, the signals is coming bidirectional, but of course we have only 2 pairs, and that we can provide the same speed of data, we need to go higher with the frequency, with the data, with the signal frequency, and this makes it for us not so easy for the design for the filters, as you will see, but you also can see that we have some solutions for that. On the right side, you see the cable. Here's the cable for the standard Ethernet, where we need to have 8 wires, and single pair Ethernet, which is only 2 wires then. Here we put together some information about difference between the standard Ethernet and the single pair Ethernet. On the left hand side, the single pair Ethernet, data rate 10 megabit per second up to 1000 megabit per second. The same with the standard Ethernet also. Like I said, 10 gigabit per second is also possible, but in the industry we have 100 megabit per second or 1000 megabit per second. The reach is really good with 1 kilometer length at least. Like I said before, normal file chips, they can even handle 1.7 kilometers, so this is great compared to 100 meters for the standard Ethernet, which is also very good. Yeah. We have full duplex mode also for the standard Ethernet, and per definition, single pair Ethernet can also be used in intrinsically safe areas. If you look inside such a machine, then we can see circuit boards, and on the circuit boards for single pair Ethernet, we can see following things. On the left hand side, this is the connector. This is the single pair Ethernet connector. It's very small compared to an RJ45, and what I said before, it's much more robust in terms of mechanically robustness. On the right hand side, we have the PHY chip. The PHY chip is changing the analog signals into digital signals, and this here in the middle, these are the magnetics. And this is where we're talking about today, about the magnetics, what kind of magnetics we need for the single pair Ethernet. By the way, this board is what we designed for ourselves in our lab. You can imagine maybe the size is the same like a checkout. What is the single pair Ethernet filtering? To come to this question, I like to show you what we found when we heard about single pair Ethernet the first time. So single pair Ethernet basically came up from the automotive Ethernet. Back in 2011, there was the company Broadcom, and they started with single pair Ethernet, but they called it broader reach, and it was more based for used for automotive applications. And this is the circuit that you can find in many data sheets of PHY chip vendors for 100 base T1 automotive Ethernet. So we have this CAM mode termination circuit here. We have a CAM mode chip here, which is very broadband, and we have here 2 filters. These are capacitors. And when you put this circuit on a circuit board, then you see it's very small, and this is the reason why it's used. But for the industry, it has a problem, and this is these the capacitors. They only provide an isolation of 50 volt, and this is okay in automotive applications. There you have a very defined area. Some engineers said some smart thing. He said, yeah, if you want to apply a camera in the automotive system, you don't open your chassis normally. Yeah, but in the industry area, it can be different. Yeah, you maybe want to apply, you want to add a camera to your system, and therefore you need to have a higher safe class. Yeah, and in the IEEE, you can find the norm, the safety norm. This is the IEC 62368-1 or the old IEC 60950-1, and therefore 50 volt of isolation are not enough. So what we can do, we also made thoughts about how we can improve this, or how we can provide an isolation here. And so we first thought, okay, we do a solution for 10 base T1, which is also valid for 1000 base T1. Yeah, so one solution for everything. But we soon figured out that this is not really possible. And the reason you can see here. Here you can see some graph from return loss and from the mode conversion loss requirements out of the IEEE 802.3 CG. Yeah, and when we measure values, then all the values should be under the curve that you can see here in blue, or under the curve that you can see here in green. Like I said, this is mentioned in the IEEE. After talking with some engineers from other companies, they told us the limit is even higher for the mode conversion loss. It normally should be minus 45 degree dB, that a signal will really be sufficient at the 1000 meters. So we have these requirements, and especially frequencies from 100 kilohertz to 1 megahertz are challenging for us. These are very deep frequency, and for the deep frequencies we need a very, very high inductance. You can see this here. What we did here is that we tried different circuits. So we built it up, first of all, the circuit for the automotive Ethernet. It's the same circuit, but what you can see here is that there's a camo choke, and this camo choke is very, very large. The reason for this, why this camo choke is very large, before you have seen the automotive Ethernet for 100 base T1, but for 10 base T1, we need a much more higher inductance. And therefore the camo choke needs to be larger. And so this is the dominant element in this circuit. Yeah, very small here. These are the capacitors. And what we did to provide then a higher isolation is that we took the same circuit, but instead of the 50 volt capacitors, we took 2 kV capacitors. And on the right hand side, we used transformers. Why we use transformers? We said, okay, 10 base T1, the data rate is approximately the same as we have for 100 base T for the standard Ethernet, and therefore we use transformers. So why not try it with transformers? And this is why we did what we did. And here you can see the results. In gray and in black, you can see the results from the capacitor solutions, and the transformer solutions you can see in red. And what you can see here, if you zoom inside at the area between 100 kilohertz and 1 megahertz, is that we are very, very close with our capacitor solution, very close at the limit of the return loss. But the transformer solution has a good distance to the limit of the IEEE. When we look at the mode conversion loss, then we are very, very good, no matter what kind of isolation we have, if it's capacitors or if it's transformers. Here, even the capacitors have a better performance. In deeper frequencies, yeah, up to maybe so something under 10 megahertz, maybe 8 megahertz or so, then the picture is changing. Then the transformer is providing a better performance. But like I said, everything is far away from minus 25 dB limit, or if we use the 45 dB limit, also there we are very much away from the limit here. Here is how this circuit is looking like for 10 base T1. On the left side, you see the PHY chip, and on the right side, you see the connector, and the filtering is in between. We have the D1. This is a TVS diode. This is just a small component, a very, very small component for ESD protection. Then we have here the transformer. This is T1. T1 is for providing the galvanic isolation, but it also can lead CAM mode signals to the ground over the middle pin. Yeah? And therefore, we don't need an extra CAM mode choke for 10 base T1L. Yeah, so the transformer has two functions here. Then we have C2 and C1. This is providing isolation to the ground. C1 even with 2 kV. And then we have a special thing, and this is capacitor C3. And this capacitor C3, this has a special function, and this is that we can improve the signal behavior in very deep frequencies. And this is between the 100 kilohertz and the 1 megahertz. If you want to build up such a circuit and you say, yeah, okay, I want to do this, but I cannot put the capacitor between two middle pins because I don't have two middle pins, then you can switch to the right solution here. You can use two capacitors instead of one, and you put them outside of the transformer, and then you will have almost the same signal behavior. After we were finished with all the design, we were very happy. Yeah, we were the first ones on the market that could provide a single per Ethernet solution on a circuit board with a good galvanic isolation. But we were in contact with IC houses, and those IC houses said, "It's a wonderful job what you guys did, but there is a but here, and this is the transmitter output group." And first of all, we thought, what is the transmitter output group? This has nothing to do with the MDI requirements. This is more a chip requirement. But we figured out that this is an important requirement also for the EMI filters. So what's this all about with the transmitter output group? To measure this, you need to take a PHY chip and put the PHY chip on test mode 2. And then you measure on the cable or directly at the connector. And you measure on two different points. And this droop on those different points, this should not be more than 10% of the voltage. And when we first tried our circuit, we had a droop of 15% or so. And in this example, it was over 10%. So it was too much. We had to do something to reduce the droop. And yeah, it took us a while, but the solution was quite simple. The solution was we have 2 points where we can provide a solution here. Point 1 is that we increase the inductance of the transformer. In this case, we have 350 microhenry. If we raise the inductance to 600 microhenry, we are good. What we also can do is that we increase the capacitance. Before we had, I think, 200 nanofarad. Now we have 470 nanofarad. And this really helped us to decrease the droop. Here you can see this on a circuit board on the right hand side. This is the capacitor. So those capacitors, they're really small and bring a solution for this problem. For the case for 100 base T1, we also made our thoughts in the same way. Here you can see the 3 circuit boards again, and there you see on the left hand side what is really the advantage when you take some circuit like for automotive Ethernet. Everything is very, very small here. The capacitors are very small. The CAM mode choke is very small. So this is really a cost-effective solution here, and it's of course less weight here. So this is really good for automotive Ethernet. If you take the capacitor solution with 2 kV, then of course the capacitors stay the same. They're still large and expensive. So we tried it also with the transformer. The difference between the circuit of the 10 base T1L circuit and this one here is that you cannot see a capacitor C3 at the middle pin here anymore. Also, you have here this CAM mode choke for the higher frequencies. The CAM mode choke here is, the transformer, like I said before, is providing a good EMI decrease, or a decrease of CAM mode signals in deep frequencies, but in higher frequencies, we need the support of the CAM mode choke. And this is the results, what you can see for 100 base T1 return loss. Here, up to a frequency of 20 megahertz, the performance of the capacitor solution is better. Here the 2 kV capacitor solution is even better than the 50 volt one, and there we have in red the transformer solution, but also the transformer solution has a comfortable distance to the norm, to the limit of the IEEE. Up to on 20 megahertz, the picture is changing a bit. Here, the transformer solution has a better performance than the 50 volt capacitor solution. Also here, if you look at the mode conversion loss, and here we worked with a 50 dB limit, then we can see that the performance of the capacitor solution with the 50 volt is not as good as the transformer solution. And when we go closer, then we see we are very close to this limit that we set up here. I need to say that we always took the same camo choke for our design. Of course, it can be improved if you use a larger camo choke, but we compare the same things together. And so you can see here the differences. By the way, now I was talking about 10 base T1L, so the long reach, the 1000 meter reach, and I was talking about 100 base T1, but many customers are also working with 10 base T1S. So for short reaches, for multi-drop, what about this? And here's good news for you. So if you build up a circuit which can handle 100 base T1, you can also handle 10 base T1. Because as you can see, these are the limits of the return loss and for the mode conversion loss. And this is a bit less harsh than for the 10 base T1, for the 100 base T1. And so you can use the same circuit here. Schematic for 100 base T1 can be used for 10 base T1S. This is the message. And in short, you see here, this is a comparison of the size of the PCB if you use a 50 volt capacitor solution, a transformer solution, or 2 kV capacitor solution here. Now we come to the topic power over data line, and as I mentioned before, this is the part of my dear colleague Simon. I will do a kind of magic switch now with Simon. Simon, stage is yours.
Hello also from my side. I will short tell you about the power over data line and our newest invention and experiments. So I think power over Ethernet is for the most customers known. So we have in power over Ethernet there's two lines here in case of 100 base TX, in which we are transferring signals in both directions. But these two lines we are also using for the voltage or for the power transmission. Here it is, you can see it is very easy. Two lines are transferring in common mode offset. But if we have only two lines over the whole application and we use it for signals and also for power, we have to go in other direction. So here we have our circuit for 10 base T1L. We have our voltage insertion, so the plus side and the minus side, and we need these two capacitors for DC isolation. So the voltage is only going, or the current is only flowing to the right side, and then on the lower line back, and not going into the circuit over the transformer or into the transformer and making a short circuit. So we have here DC isolation. According to the IEEE, we need not, this is not an additional, but we need an isolation of 60 volts. So in this case, we have to implement these two capacitors C3 and C4 to prevent if someone is using some voltage that our device is then short circuiting and destroyed. In this case, we use 470 nanofarad for 100 volts isolation. So in summary, it is 200 volts isolated, or if we using there for every capacitor 60 volts, then it's not so easy derated. You can see it on the right side. If we have on every capacitor 25 or 24 volts, then it is only decreasing at 16% of its value. If we would go only with smaller capacitor, then it would be not so enough for the signal transmission. So we choose the 470 nanofarad for our signal transmission. But for power over data line, we have to implement also the power path. So here is the circuit for signal transmission, and for power transmission we are implementing this choke L2 and our power source V1. After we developed the first prototype, we found out that the return loss are very good, but then we looked into the mode conversion and we found that we are over or worse than the limits, but these are the stricter limits which are not mentioned in the IEEE, but like Martin said, it was not this 25 or 30 dBs, but 45 or even higher. So we are violating them at the mode conversion. And now it was our search to find a solution for this violation. We improved it by implementing the L1 comb mode choke into the signal path, and then we found out there is some problem in this structure because there is a patent from Broadcom from the automotive Ethernet from 100 base T1, and yeah, this is a problem, not a problem for us, but mainly for the customers when they are using this. So they have to consider this, or we give you an alternative in which you are not using these two capacitors, C3 and C4, but using only one at the center point, the C3. And so you have this alternative circuit design. And of course, we are tested it also to see if it is equivalent to the other one. And here are the results for return loss. They are very good. And also for mode conversion, we are near the same. There are only several millidBs, or yeah, depending on how you measure this, but they are comparable. So you can use both versions of the circuit design. Also, the droop simulation, this was what Martin told, was also very good because we are under the 10%, which is necessary in one of in the IEEE. So it was also quite good. But then 2022, we developed a new design. So on the left side, you see the old one with the 700 milliamp choke, and which were possible for the Poodle classes 0, 2, and so on. So missing Poodle class 1, Poodle class 12, and Poodle class 15. But then we looked for our other chokes and for another design, and we developed a new new circuit, and we used other components. And in this case, we are it's possible for us to cover all the Poodle classes from 0 to 15 with up to 1.6 amps. Here you can see from our experiments and calculations. So it is not only a calculation and simulation, but this is real experiments. We are measured 70 meters for this one, and for the right one, this was a real measurement. We measured up to 100 meters and 30 watts transmission, and up with the AWG 22 cable. So it is possible to use this design for this Poodle class, for Poodle class 8, but also for other Poodle classes. And the only difference here is, not the only, there are three different parts. So the combo choke on the L1. So here on the right side, this is the L1. We increased it because we have to be sure that 1.6 amperes flow through it and do not destroy it. So on the left one, it is at the time the smaller one, it is not capable. So if we want to improve this design also to more than 700 milliampere, we have to use also this big one. And yeah, the transformer T1 is in this case decreased. We see on the left side it's a big one, on the right side it's smaller. And for the choke from L2 in size 1280, we are decreased it to 1090, so 10 by 10 and 9 millimeters in height. Interesting is we can now cover all the power classes, and you see this in the next slide here. We have the missing Poodle classes also covered here on Poodle class 15 up to 1.579 amps within transmission power or within power transfer of 52 watts. And it is not only that we calculated it, but we have also our evaluation boards from analog devices here at the company, and we tested all the designs. We tested it with several volts, not up to 50 volts, but up to 1.6 amperes with other voltage classes. And yeah, it was working. And at the time we are already not finished, but yeah, in future we will show you all the results and give you some recommendations and some examples how you can build up your Poodle circuit up to Poodle class 15. It would look like this one. In the upper corner you have your Poodle choke. In this case it's the older design. In the newer you have then this little bit smaller. Here you are smaller, so that you can cover an size of a credit card also with Poodle up to 1.6 amperes. So it is quite small but very powerful, and you can transmit this 1.6 up to 30 meters, or depending on the cable you are using it, also longer. One small new info is the 1000 base T1. We are also working on it, and here we have covered also the IEEE limits up to 600 megahertz with our new design or new components we found, which are capable to transmit 1000 base T1 or the speed of 1000 megabit. And also not for the return loss, it looks good, but also for the mode conversion. I think you can see there is some violation at the bottom side, but it is very close to the limit, so it will take us a little bit time, and then then it's possible to have a very smooth and beautiful curve, that there is no violation. And this would be in next month some newest. Be interested, go onto our website, look for some news. We will inform you if we have a better solution than this one. Yeah, we have also our landing page, our webinars. You can also go to there and look for the past or informations which we are have there. Also our app note about single pair Ethernet. You can also find it on our website. Please go and download it, and if you have questions, you can ask us, or now is also the time to ask the questions. We are here and want to answer you.
Yeah, so thank you very much, Simon, and also Martin, for your interesting presentation. Yeah, as you have mentioned it, now we would like to turn our attention to your questions. And yeah, there were also a lot of questions come in the meantime. So yeah, interesting topic. So yeah, let's start with the first question. What about 10 base T1s? Is there a solution there yet too?
Do you mean 10 base T1S?
Yeah, 10 base
okay.
T1S. Yeah, sorry.
Yeah, I think Martin mentioned it also before. He goes a little bit faster over this topic, but there is some solution. You can use directly the 100 base T1 design for 10 base T1S, and maybe also depending on your circuit, you are using Poodle or not. you can use it directly or ask us. We can go over this and talk, get in talk with you. But there is the solution available. Yeah.
Okay, thank you very much for the explanation. And then, yeah, let's come to the next question. Are there Poodle controllers also yet?
Yeah, this is a very common question. Lots of the customers asking us because you cannot use a Poodle design without a Poodle controller. So yeah, we get some informations from the IC houses. There will be a Poodle controller in next time. So be also informed if you're looking on the website of the Poodle of the companies like Analog or Texas Instruments. I cannot say which date would be some new release of them, but yeah, there will be in next future one of them.
Okay, thank you very much. Yeah, then let's go on with the next question. On the Poodle overview on page 53, there was an 47 microhenry coil on it for the 2022 design. Why is it 10 times smaller than the 2021 design?
Okay, I think you mentioned this one and this one. Yeah, I think, yeah, here you can see on this on the article number that yeah, in reality it is smaller than this one. And also, if you look on the picture, yeah, the left Poodle choke has has 470 microhenry. The right one has only 47. It is because of the IEEE limits has lowered. There was an at the IEEE meetings, and yeah, they asked for lowering the limits, and because of this, we are capable to use smaller inductors. And like I mentioned, I measured this with our student in the lab. We are used different chokes. We are used higher than 47. We used 68, 100, but we try to go to the lowest limit and try it to work with it, and 47 was very good to work with it, also with 1.6 amps. So it is possible because of the PHY chip. They are capable to work with this low microhenry.
Okay, thank you very much, Simon, for your explanation. Then let's go on. I think we have time for one more question, and it is, how can I get the components you used for the 1000 base T1 design? Are they available yet?
Yeah, it's also a good question. We have the components. They are not a new invention, but we have that already on our website. So if you have you want to build up a 1000 base T1 circuit, then go in contact to us to the write us on the website or directly. Here you can also write us, and we will provide you the components or the number of the article number, and then you can buy it directly and use it for the circuit.
Okay, so thank you very much, Simon, and also Martin, for your interesting presentation today. At least I found it very interesting. Hope also all our attendees took some with them. So I think there are still some questions open. I see them, but we will answer them later on via email. And also, if you have any other questions left, just email us at exhibition@we-online.com, and we will try to answer all your questions promptly. So thank you very much for your attention. Also, quick hint, because we will start our next presentation in I think the next 15 minutes, and the presentation is about high frequency, common mode, noise, and solutions. And that's why we also have to close this session now. So thank you very much again. I hope you enjoy our digital days. Goodbye.
Yeah, goodbye.